Welcome back to the deep dive. Today we are embarking on, well, the ultimate origin story. It's a journey that starts right here, with something as simple as the pie on your table.
Or the hand you're holding it with.
Exactly. We're inspired by this amazing Mark Twain quote where he's looking at the stars and wondering if they were, quote, made or only just happened.
And we think we can answer that. Our mission, really, is to trace the history of every single atom that makes up you, or that apple pie.
The famous saying comes to mind. To make an apple pie, you must first invent the universe.
Right, and we're going to unpack that. We're talking about the carbon, the oxygen, the iron,
Mm-hmm.
all the heavier elements that weren't made in the Big Bang. They had to be cooked somewhere.
In these cosmic kitchens we call stars. So we're going from the tiniest parts of matter, the atom, all the way up to the most violent forces in the entire cosmos.
Quite a trick.
Okay, so let's start with that apple pie. If you start cutting it in half over and over, the old Greek idea was you could just do that forever, right?
Yeah, an infinite regression. But we know now that's not true. The process stops.
After how many cuts?
It's about 90. After 90 successive cuts, you're down to a single, indivisible atom.
And what physicists figured out around 1910 in places like Cambridge is that the atom isn't just a tiny solid ball.
No, not at all. It's mostly defined by this cloud of negatively charged electrons on the outside. They're what determine all of chemistry.
The color of things, the texture, how things react.
Everything. And then deep inside you have this tiny, tiny little nucleus.
With the positive protons and the neutral neutrons, but you say tiny, and you mean really tiny.
I mean, it's 100,000 times smaller than the atom itself, which means the atom, and by extension this table and you, it's all 99.99% empty space.
Which is the big paradox, isn't it? If my elbow is mostly empty space and this desk is mostly empty space, why does my elbow just slide right through it?
It's a fantastic question, and the answer is the power of that electron cloud. It's all about electrical forces.
So the outside of every atom is negatively charged.
Exactly. And negative charges. Well, they repel other negative charges. Fiercely.
So the electrons in my elbow are pushing away the electrons in the desk.
With incredible force. That repulsion is what creates the illusion of solidity. If you could somehow switch off electricity, everything would just collapse into a diffuse cloud of dust.
That's mind-boggling. The chair I'm sitting on isn't solid. It's just angry electrons pushing back.
In a nutshell, yes. The strength of the commonplace is just astonishing.
Okay, but what if we cut deeper? What if we actually slice into that nucleus?
Now you're doing something completely different. You're not just getting a smaller piece. You're transmuting the element. You crack a carbon nucleus, change its number of protons.
Yeah.
It's not carbon anymore. Maybe it's helium.
Which was the dream of alchemy, right? Turning one thing into another.
The dream of turning lead or copper into gold, yeah. And while they never did that, their search, it basically laid the foundations for modern chemistry. We found all 92 of the naturally occurring elements because of that pursuit.
And the fact that some elements, like oxygen or iron, are way more common than others, like gold, that's a clue.
That's a huge clue. Their abundance tells us a story about where they came from.
Okay, so let's stick with that nucleus. It's packed with protons, which are all positively charged.
Right.
And positive charges should be repelling each other violently. So what holds the nucleus together? What stops it from just flying apart?
You need a stronger force. And we have one. It's the fourth fundamental force of nature, the nuclear force.
The strong nuclear force.
You can think of it like super powerful hooks. But they only work at incredibly short ranges, when particles are practically touching.
So it overwhelms the electrical repulsion.
Completely. And the neutrons are key here. They act as a kind of glue, adding more of that attractive nuclear force without adding any more of the repulsive electrical charge.
But to get two nuclei close enough for those hooks to grab on, you'd have to overcome that initial electrical repulsion.
And that takes a staggering amount of energy. You need temperatures in the tens of millions of degrees.
Conditions you only really find in one place.
The interiors of stars, that's why the universe is still, 99% hydrogen and helium. Making the other stuff is incredibly hard work.
And that leads us to our own star, the sun. Stars are born when these huge clouds of gas and dust just collapse under their own gravity.
Right, and all those collisions heat things up until the core hits that magic number.
And then what happens?
Thermonuclear fusion ignites. 4 hydrogen nuclei get smashed together to form one helium nucleus. In that process, a little bit of mass is converted directly into energy. a gamma-ray photon.
And the sun's been doing this for 5 billion years, converting 400 million tons of hydrogen into helium.
Every single second.
That number just breaks my brain. 400 million tons. And that photon, the light from that fusion, it takes an incredible journey to reach us.
Oh, it's an epic journey. It's born in the 40 million degree core, but it doesn't fly straight out. It gets absorbed, re-emitted, it bounces around for, well, it can be a million years.
A million years to get from the core to the surface.
Before it finally escapes from the relatively cool 6,000 degree surface and travels to us as visible light.
But that fusion reaction releases another particle, doesn't it? Something much weirder than a photon.
Yes, the neutrino, the ultimate ghost particle.
It has no weight, no charge.
Well, we now think it has a tiny bit of mass, but for all intents and purposes, it's a ghost. A billion of them are passing through your eyeball and the entire Earth every single second.
And they don't interact with anything, which made them almost impossible to detect. But scientists tried, didn't they, with the home-state mine experiment?
They did. They took these enormous tanks of cleaning fluid, basically chlorine, deep underground to shield them from other radiation.
And the idea was that every now and then, a single neutrino would hit a chlorine atom and turn it into argon.
And they could detect the argon, but here's the mystery. They only found about a third of the neutrinos they expected. The sun was dimmer in neutrinos than our theories predicted.
So what did that mean? Was the sun's engine failing?
That was one possibility. That the sun's fires were temporarily banked. The other, which turned out to be the right one, was even stranger.
That the neutrinos were changing.
Exactly. That they were changing their flavor, as we say, on their 9-minute journey to Earth. This discovery just. It turned particle physics on its head and opened up this brand new field of neutrino astronomy. We can literally look inside a star's core now.
But even the sun's engine won't run forever? In what, 5 or 6 billion years, the hydrogen in the core is going to be gone.
It's all been converted to helium ash. And when that happens, the star enters a new phase. The core contracts, heats up even more until the helium itself ignites.
A second round of fusion.
A second round, fusing helium into carbon and oxygen. The star rises from its own ashes like a phoenix, but for any planets nearby, it's a catastrophe.
This is the red giant phase.
Yes. The sun's outer layers will swell up and cool down, becoming this huge, bloated, ruddy star. It'll swallow Mercury, Venus, and almost certainly Earth.
Our oceans will boil away, the atmosphere gets stripped.
It's a grim picture. After that, the sun will start to pulsate, gently blowing its outer layers off into space.
Creating those beautiful shells of gas we call a planetary nebula.
Which is such a misleading name. It has nothing to do with planets. It's just the ghost of the sun made of all that new carbon and oxygen it created.
And what's left behind?
The core. A tiny, hot, incredibly dense object called a white dwarf.
Where a teaspoon of it would weigh over a ton.
At least. And that just sits there and cools for trillions of years, eventually becoming a cold, dead black dwarf.
But sometimes a white dwarf can flare back to life, right? A nova.
Right, but only in a binary system. If it has a red giant companion, it can pull gas off its partner. That hydrogen builds up on the white dwarf's surface until, bang, it all fuses at once. A brilliant flash. A nova.
But that's very different from a supernova.
Oh, completely different. The fate of a star is all about its mass. And for stars much, much more massive than our sun, the end is faster and far more violent.
They burn through their fuel, cooking up heavier and heavier elements. Neon, silicon.
All the way up to iron. And iron is the end of the line.
Why iron?
Because fusing iron takes more energy than it releases. It's a fire that puts itself out. The star can no longer produce energy to fight against gravity.
So gravity wins.
Instantly and catastrophically. The iron core implodes in a fraction of a second. The outer layers crash down, rebound, and you get a supernova. An explosion so bright it can outshine its entire galaxy.
And we've seen these. The guest star of 1054.
Recorded by Chinese and Anasazi astronomers. It was visible during the day for 3 months. What's left is the Crab Nebula. The proof is right there in the sky.
After that explosion, what's left of the core depends on mass again, if it's under a certain limit.
About 5 times the mass of our sun. The collapse stops. Gravity has crushed the electrons into the protons, creating a star made almost entirely of neutrons. A neutron star.
An object the size of Manhattan.
Spinning 30 times a second.
And if its radiation beam sweeps past Earth, we see it as a pulsar.
Exactly. And the density is just, we said a white dwarf was a ton per teaspoon, a neutron star. You're talking about the mass of a mountain in that same teaspoon. It really makes you respect the stability of, everyday objects.
But if the core is even more massive, Gravity's victory is absolute. The collapse doesn't stop.
It just keeps going. The star shrinks and shrinks until its gravity is so strong that nothing, not even light, can escape.
A black hole.
The Cheshire Cat vanishes, leaving only its gravitational grin behind.
And we found these. The Uhuru satellite found Cygnus X-1 in the 70s, this flickering X-ray source, an unseen companion 10 times the sun's mass, pulling on a visible star.
It could only be a black hole, and that's where you get into some really wild ideas. Wormholes, gravity tunnels through space-time. It's just incredible.
And this all brings us back, full circle, to us, to life on Earth. All these processes, from red giants to supernovae, they are connected to us in, what, 4 really profound ways?
4 pillars of connection. Let's walk through them. First, simply matter.
The atoms in our bodies.
The calcium in your bones, the iron in your blood. Every single heavy atom was forged in a red giant or a supernova and scattered through the galaxy. We are literally made of star stuff. Our sun had to be a second or third generation star.
Okay, that's one. What's the second pillar?
The trigger. The birth of our solar system itself was likely kicked off by a nearby supernova. The shock wave from that explosion compressed a cloud of gas and dust and started the collapse that formed our sun and planets.
Wow. So a star had to die for our sun to be born.
In all likelihood, yes. Third is energy. We are solar powered. Life on Earth runs almost exclusively on sunlight. Photosynthesis, the weather, it's all the sun.
And the last one.
Evolution. The raw material for evolution is mutation. And the significant number of mutations are caused by cosmic rays high-energy particles that are shot across the galaxy by, you guessed it,
Supernova explosion.
supernova explosions. The deaths of stars thousands of light years away are directly linked to the evolution of life right here.
So we've gone from the atom to the nuclear glue, through the life and death of stars, to white dwarfs, neutron stars, and black holes. All to find out that we aren't just living in the cosmos.
We are children of the cosmos. We are born from it.
It's humbling. You know, our ancestors worshipped the sun. They saw its power. But when you realize the sun is just an average, maybe even mediocre star.
Compared to the truly massive stars that forged us, or the black holes that bend reality.
What does that do to our sense of awe?
It expands it, I think. It shows that astronomy isn't just about looking at distant lights. It's about understanding the terrifying, beautiful, and bizarre forces that created the ground beneath our feet and the very thoughts in our heads. The awe is right here.
A perfect thought to end on. Thank you for joining us on this deep dive into the stellar origins of everything. We'll see you next time.